Hello and welcome to our first session of Reservoir Engineering courseware brought to you by Das Scientific Research Labs Private Limited. So our first session will be about properties of reservoir fluids, and we will see the classification of the reservoirs based on the properties of fluid they contain, and also we will look at different methods through which you can determine these fluid properties. For further reference, you can refer to Craft and Hawkins chapter 1. So there are four types of hydrocarbon reservoirs based on the state of fluid in them. They can be described with respect to a pressure temperature phase diagram, and their names are single phase gas reservoir, retrograde gas condensate reservoir, dissolved gas reservoir, and two phase reservoirs. Now I said with respect to phase diagram, so let's have a look on them. So this is a typical pressure temperature phase diagram. This horizontal axis is of temperature, it's in Fahrenheit. This vertical axis is of pressure in PSI, pound per square inches. Okay, and these are these various curves you are seeing because the oil we generally found in the reservoir, it's a mixture, it's not a pure substance. Okay, so let's start with the 0% line. Okay. So this curve which you are seeing, it's called the dew point curve. Okay, at this point, and it's marked with 0%, it means that it's the 0% liquid line. Okay, so at the right hand side of this curve, at any point the reservoir fluid would be single phase gas. Okay, so and at this point the liquid and gas phases will coexist, but basically if it's a gas reservoir and we start dropping the pressure, okay, so at some point it will intersect this point, and at this point liquid and gas phase could coexist, and beyond this point the mixture will contain 0% liquid, it will be single phase gas. And so as we move left, we see 10% liquid line, 20% liquid line, 30%, 40, 50, 60 and up to 100%. Okay, so as we move left from the dew point line, we can see the liquid percentage in the mixture increasing. So this entire region is called the two-phase region, and then the final line, the 100% liquid line, it's called the bubble point curve. Okay, so on the left hand side of this bubble point curve, or according to this figure on the top of this curve, okay, at any point the reservoir fluid would be single phase liquid, single phase oil, no gas cap. Okay, then there are a few important terminologies you need to understand. This line we are seeing, the vertical line, the bottom point of this line is called the critical point. Okay, so critical point is the point where the dew point curve and the bubble point curve meet. Okay, and at the pressure and temperature at this point we call it the critical pressure and critical pressure. The next thing you need to see is a Cry-Condon therm. Okay, so this line, the line which just appeared, it's called the Cry-Condon therm. Okay, it's the maximum temperature at which both the liquid and gas phases can coexist. It's the maximum temperature at which we can have a liquid and gas coexist. Beyond this temperature, no matter what the pressure is, it will be either single phase gas or single phase liquid. Two phases will not coexist. Then similarly, there is a bar for pressure also. It's called Cry-Condon bar. Okay, so this orange line which you are seeing, it's called the Cry-Condon bar. Okay, and if the pressure is above the Cry-Condon bar pressure, then no matter what the temperature, the reservoir fluid will be either single phase liquid or single phase gas. Both the phases cannot coexist. Okay, and so basically it's the critical point line by which you can distinguish if it's a single phase liquid or single phase gas. If we will see this later. So let's get back to the presentation. Okay, so if the reservoir temperature and pressure are such that they lie outside the two-phase region and lie on the right hand side of the Cry-Condon therm, then the reservoir is a single phase gas reservoir. Now let me explain this with respect to the phase diagram. Okay, so this is our phase diagram. Okay, we don't need the Cry-Condon bar for now. We need the Cry-Condon therm, and we need a single phase gas reservoir. Okay. So now we have the critical point. This is the critical point. Okay, this is the Cry-Condon therm, and this point on the top, let's call it A. So this point, if the reservoir pressure and temperature are same as that of this point, or at any point in this region, on the right hand side of the cryocondensate drum and on the outside the two-phase region, then at this point the reservoir fluid will be a single phase gas. Okay, and the reservoir would be called a single phase gas reservoir. Okay, now you will ask why the dotted line. So when we produce from a reservoir, we are basically withdrawing the fluid. So at reservoir condition, we assume the temperature to be constant. Okay, so like temperature at this point is 270°F. So we will assume this temperature to be constant for the reservoir. Okay, so as we produce from a single phase gas reservoir, we are withdrawing gas. So the pressure of fluid in the reservoir is dropping continuously. Okay, the temperature is constant, but the pressure is dropping. Okay. So it will drop and drop, but it will the reservoir fluid, and assume this to be the abandonment pressure 1500 psi. Normally it's much lower than 1500 psi for practical purposes, but in this particular phase diagram we don't have pressures below 1300 psi. So let's assume 1500 psi to be the abandonment pressure. So this is the path along which the fluid, the single phase gas reservoir gas would travel at reservoir conditions. Okay, so the entire time, during the entire production period, the reservoir fluid pressure and temperature never crosses the two-phase envelope. So the reservoir fluid will remain single phase gas for the whole time. Okay, it will never have any liquid content. But on the surface, now let's look at the fluid which we will achieve at the surface. So while traveling from the reservoir, from the bottom of the well to the surface equipment, the temperature and pressure both drop. Okay, so this path, let's call it A and this point A2. This path will be the path followed by the produced fluid. Okay, so as it moves along the wellbore, the pressure and temperature both drop. So it will follow this curved path. Okay, and at finally this point, as you can see, at this point A2 is inside the two-phase region. So this the fluid which we will receive on the surface, it will be partially liquid and partially gas. But the point to note is both the liquid phase and the gas phase will have the same composition. The fluid which we are receiving at the surface will have a liquid phase and a gas phase, but they both will have the same composition. Okay, so this was about single phase gas reservoirs. So everything I just explained is written in the slides. So during the production, the pressure drops in the reservoir. However, the reservoir temperature remains constant. So the reservoir fluid follows path A1 during production. That vertical line I showed in the phase diagram, I will show it again. This is the path A1. This is the path of the reservoir fluid, the fluid which remains in the reservoir. Okay. So, but along the wellbore, the fluid which is produced along the wellbore, along the wellbore, the temperature and pressure both decline. Okay, in the reservoir, only pressure will decline, the temperature will remain constant. But along the wellbore, both temperature and pressure will decline. Hence, the fluid produced at the surface will follow path AA2. This curved path is called let's call it the path AA2. This point is A, this point is A2. Okay, and it intersects the two-phase envelope at this point. Okay, so the fluid which we will be receiving at surface, that will be two-phase. That will be in two phases. It will be part liquid and part gas. Okay. AA2 crosses the two-phase envelope. The produced fluid may be in two phases, gas and liquid. Okay, but the composition of fluids will be same. The composition of the gas phase will be same as the composition of the liquid phase. This is a very important point. Okay, hence a condensate liquid is produced at the surface, but the reservoir fluid remains in single phase gas state the entire time. The reservoir fluid never goes into liquid state. Okay. So next we will see the retrograde gas condensate reservoirs. Okay, so if the reservoir pressure and temperature are such that they lie outside the two-phase region and lie on the left hand side of the cryocondensate and lie on the right hand side of the critical point. Okay. Then the reservoir is a retrograde gas condensate reservoir. So now let me explain retrograde reservoirs with a phase diagram. Okay. So we have already seen single phase reservoirs, so I will remove them. No single phase reservoir, no A2. Okay, so we need to see retrograde gas condensate reservoirs. Okay. So this yellow line, the top yellow point, let's call this point B. Okay, so this point B, it's outside the two-phase envelope. It's on the left-hand side of the cryocondensum and it's on the right-hand side of the critical point. Okay, so this any point, any pressure temperature combination lying inside this region, okay, it will be called, it will represent a retrograde gas condensate reservoir. Why retrograde? Because when we start producing, okay, from now onwards, for the remaining kind of reservoirs, we are not much concerned with the kind of fluid we get on the surface, okay, because in any case it will be part liquid and part gas. Okay, so we will only focus on the phase behavior of the fluid in the reservoir, not of the fluid coming to the surface. Okay. So let's say the reservoir was initially at point B. Okay, so the point B is on right of the left of the cryocondensum and right of the critical point and outside the two-phase envelope. So it will be initially single-phase gas. Okay, but as we start producing from the reservoir, okay, the pressure will drop, but the temperature, like we said earlier, it will remain constant. So as the pressure drops, it will reach here. This point is let's call it B1. Okay, this was B, this was B1. So at B1, the path of the reservoir fluid crosses the two-phase envelope. It crosses the dew point line. Okay. So now at the reservoir, a condensate liquid will start to separate out from the gas phase. Okay, and this will be happening at the reservoir. Okay. So now what will happen as we move further? This liquid percentage would be increasing. Now the thing is that there is a liquid separating out from the gas in the reservoir. That liquid will stick to the pore walls. Okay, and in any porous medium, a liquid moves until and unless it achieves a certain minimum saturation. We call it the residual saturation or immobile saturation. Until and unless that saturation is achieved, the liquid phase will not move. Okay. So what we will get at surface, okay, until this point it will be more or less same as the single phase gases reservoir. We will get part liquid, part gas, and they both will have the same composition. But when the reservoir fluid enters the two-phase region, okay, now some liquid has started to separate out from the gas in the reservoir. Okay, in the reservoir, this is happening in the reservoir. So now the composition of the gas in the reservoir is changing. Okay, so what the fluid which will be we will achieve at the surface, which we will get at the surface, it will have a lesser liquid content. Okay, and by the way, in oil and gas industry, we are mostly considered with the liquid oil. We are not much considered with the gas nor the water. Okay, we want liquid oil in petroleum production. Okay, that is favored. So now there will be the liquid amount received on the gas will be lower. Okay, so that's a disadvantage. Okay, but then as we produce further, the pressure drops down further in the reservoir, and it reaches a point where the liquid percentage is maximum. Okay, it reaches a point where a liquid percentage is maximum, and after that, if we drop the pressure further, then as you can see in the phase diagram, the liquid percentage will start to reduce. This was the maximum. This was the maximum liquid percentage that will be achieved in the reservoir. Okay, but after that, the liquid starts to vaporize as we drop the pressure further. Now, why the term retrograde is used? Because generally, when we expand, when we reduce pressure, then vaporization should occur. You can imagine it from the gas laws. Okay, when we expand, when we reduce the pressure, we are doing isothermal expansion. Okay, so in isothermal expansion, vaporization should occur. But in this case, instead of vaporization, condensation is happening. Okay, so this is a exceptional phenomenon. Okay, this is abnormal. That is why the term retrograde condensation is used. Okay, Okay, so until this point, there will be condensation. Okay, and after this point, the vaporization will start again. So now the liquid the amount of liquid which we are receiving at the surface, that will also increase. So until between B1 and let's call this point B2, the surface gas oil ratio would be increasing, and below B2 to B3 the surface gas oil ratio, the ratio of gas received at surface to the ratio of oil received at surface, that will be increasing. Okay, so but then compared to single phase gas reservoir, there is a overall liquid loss. Okay, so that's the disadvantage of retrograde gas reservoir. There is a liquid loss. Okay, and we want liquid. Anyway, so what I just explained is written in these slides. Okay. So the reservoir fluid is initially in single phase gas state. During production, the pressure drops in the reservoir. The reservoir fluid follows path B, B1, B2, B3. Okay, this point is B. This point where it intersects the dew point curve is B1, and this point where the liquid is maximum is B2, and this point, let's call it the abandonment pressure. Okay, so this point is B3. Okay. So the reservoir fluid enters the two-phase region at B1. I just showed you this in the phase diagram. Below that pressure, a liquid condenses out of the reservoir. The gas phase is left with a lower liquid content, and the condensed liquid adheres to the wall of rock poles. The liquid is immobile until a certain minimum saturation is achieved. Okay, the gas produced at surface will have a lower liquid content. The producing gas oil ratio, so the producing gas oil ratio rises. The amount of gas is more, the amount of oil is less, so the gas oil ratio will increase. Okay. At point B2, let me remind you, this is the point B2, this was B1, this is B2. B2 is the point of maximum liquid in the reservoir. Okay, the liquid volume is maximum in the reservoir, so the retrograde condensation process will continue till point B2. We are using the term retrograde because there is condensation instead of vaporization during isothermal expansion. Okay, thus vaporization occurs during isothermal expansion, hence the term retrograde is used. Okay, this is condensation, not vaporization. So the composition of produced fluid changes after dew point. The composition of remaining reservoir fluid also changes. Okay. Hence there is a small right shift in the two-phase envelope. Let me explain that. So when the liquid starts to separate out in the reservoir, and then the product which we are receiving at the surface, okay, it has a different composition. Like in single phase, the liquid phase and gas phase have the same composition, which we are receiving at the surface. But in this case, they are of different compositions. Okay, so the fluid in the reservoir, it also has the liquid phase and the gas phase. So they are of different compositions. So the composition of gas in the reservoir has changed. So this envelope will shift slightly to the right. Okay, this envelope which we are saying, it will shift slightly to the right. We have not shown this on the phase diagram, but you can imagine it. Okay. So vaporization of retrograde liquid occurs from B2 to B3, the bottom 2 points. Okay, where B3 is the abandonment pressure. This revaporization increases the liquid recovery. Okay, so the gas oil ratio decreases at surface, and this is what we generally want. We want a lesser gas oil ratio. We want more oil and less gas. Okay, so the overall retrograde loss will be greater if for lower reservoir temperatures, higher abandonment pressures, and for greater shift in the phase diagram to the right. Now I leave this for you to imagine why. Okay, you can see this in the phase diagram and you can conclude why. Okay. So the next kind of reservoirs which we will be seeing is dissolved gas reservoir. Okay, or bubble point. They are also called bubble point reservoirs or single phase oil reservoir. Okay, so if reservoir temperature pressure are such that they lie outside the two-phase region, okay, lie on the left hand side of the critical point, then the reservoir is a dissolved gas reservoir. Now let me show dissolved gas reservoirs in the phase diagram. You don't need the corresponding from now. Yeah, dissolved gas reservoir. So this point lies on the left hand side of the critical point and is outside the two-phase envelope. So any point in this region, okay, any point in this region will represent a dissolved gas reservoir. Okay, so initially the reservoir fluid in a dissolved gas reservoir, it's a single phase oil, no gas cap, only oil. Okay, and then as we start producing, okay, the pressure drops until some point. The reservoir fluid remains single phase gas. At surface we will always receive the fluid in two phases. It will be part liquid and part gas. For now we are not considering water. Okay, otherwise it will be in three phases: gas, oil, and water. Okay. So initially we will receive gas and oil. Okay, but the reservoir fluid will remain in a single phase liquid state. Okay, until we reach this point. Okay. So let's call this point C and this point C1. Okay, so C1 is called the dew point, bubble point. Okay, so at C1 the two phases, C1 lies on the bubble point curve, so that means the liquid and gas phases will coexist. Okay, and at point C1 the reservoir fluid enters the two phase region. So from here onwards gas bubbles will start to appear. Okay, so as you drop the pressure further, the amount of gas will be increasing in the reservoir. Okay, more and more gas will come out, and it will form a free gas phase. Above the oil phase, it will form a free gas phase in the reservoir, and on the surface we will receive oil and gas only. But except in this case, as the pressure drops, the quantity of gas will be always increasing and the quantity of oil will be always decreasing. Okay. In the previous case which we saw, it was retrograde reservoir. Let me remind you, in retrograde the quantity of oil will be first decreasing and then increasing. Okay, and it will be opposite with the gas phase. The quantity of gas will be first more, then less. Okay, but in a dissolved gas reservoir, once the pressure goes below the bubble point pressure, this point can be called bubble point, and the pressure at this point can be called the bubble point pressure. So once the pressure goes below the bubble point, okay, and we keep producing, so the amount of gas at the surface will be ever increasing and the amount of oil at the surface will be ever decreasing until we stop production. At this point, let's call it C3. C3 would be the abandonment pressure. So what I explained is written for you in the slides. So the reservoir fluid is initially single phase liquid state. As the pressure declines, the bubble point will be reached. Below this point, bubbles of free gas phase will appear. Okay. Eventually, the free gas evolved will flow into the wellbore, and the flow of gas will be in ever increasing quantities. It will be always increasing. Okay. Conversely, oil flows in ever decreasing quantities. Okay. So at depletion, much of the unrecovered oil remains in the reservoir. So the oil is really less mobile compared to gas. That is why the flow of gas is more and the flow of oil is less. So on the phase diagram, the path of reservoir fluid is CC1. I just showed you. CC1 crosses the two-phase envelope at the bubble point. Okay, C1 bubble point. Okay, this is the bubble point and it enters the two-phase region. The volume of oil will be decreasing as the pressure drops. The volume of oil produced at the surface or at the reservoir. The answer is both. The volume of oil will be decreasing at the surface as well as in the reservoir as the pressure drops. Okay, because of compressibility and stuff, which we will see later. Okay, the last kind of reservoirs we need to see are two-phase reservoirs. So the condition for two-phase reservoirs is simple. If the reservoir temperature and pressure are such that they lie inside the two-phase envelope on the PT phase diagram, it would be a two-phase reservoir. So let's have a better look at them. Okay, so this green line, this point, let's call it D. Okay, so D lies inside the two-phase envelope. So any point inside the two-phase envelope, if any of the points representing the pressure and temperature of the reservoir fluid is inside the two-phase envelope, then the reservoir is a two-phase reservoir. Okay, so the reservoir fluid will be in two phases right from the beginning itself. The reservoir fluid between two phases, it would be part liquid and part gas. Okay, so as the pressure is reduced, production starts, and the pressure is reduced, so the liquid percentage will decrease. Okay, liquid percentage will decrease. Like initially it was 30% at this point, and then at this point it will be 20%. So the liquid percentage would be decreasing. Okay, in the reservoir as well as in the fluid produced at the surface. So again at the surface we will get partly liquid, partly gas, but the flow of gas will be increasing and the flow of oil will be decreasing. So it will consist of a liquid oil zone overlain by a gas cap. Gas has lesser density at oil, so oil will be on the top and liquid will be at the bottom. Okay. So compositions of oil and gas zone will be different. Every time in a reservoir we see a oil zone and a gas zone, then we should know that their compositions will be different. Okay, be it in retrograde, be it in a dissolved gas reservoir, or be it in two-phase reservoir. Okay, single phase gas reservoir, that's not a problem. Okay, it's always gas. So there never will be a liquid zone, so there will be no variation in the composition. Okay, but other than single phase gas reservoirs, in every kind of reservoir, when there is a gas zone and oil zone inside the reservoir, their compositions will be different. Okay, so the liquid or oil zone will be at its goal point, and the gas cap will be at its dew point, and it may be retrograde. So this means that the liquid zone will always be at its goal point. That means if you drop the pressure even a little bit further, okay, then more gas will evolve, more gas bubbles will form. Okay, and the gas cap, the gas phase will be at its dew point. So that means if you increase the pressure a little bit, then more gas will dissolve into the reservoir or the volume of oil will increase. Now we will start reviewing the rock properties, but let's take a 2-minute break first.